So if X is a the problem is the board, not with the chart. Right. It's not, yeah, tough enough. No. X is a type random variable on some omega F. So you have a probability space and you have a random variable defined on that. Okay. And if you have a function x to r to r, then we prove we notice nothing is a proof. F of x is also a random variable. If you have, in general, if the space is discrete, if omega is discrete, if it is finite or countable, then there is really nothing to prove. This is just composition of function. This just means f composed with x. So this is just composition of function. But if it is continuous, then you have to verify further that the f of x equal to some x naught. Some x is an event. It's in the sigma algebra. But then you can write this as this is equal to x in f inverse of singleton x or y, whatever. Okay. And then you can write it as union of x and f inverse of x equal to x, where x is in f inverse of, call it y, f inverse of. You can write it like that. So this is okay. F of x, x in f inverse y, singleton y. Maybe I should write it as that. I mean, f inverse y doesn't make sense. Huh? What? Inside the set, x is equal to x. Yeah. Initially, I wrote element of the, yeah. Okay. These sets are in sigma algebra. This is union of such sets. When you have different points, they are disjoint. So that's in the sigma algebra. So because of that, it follows. Okay. This will do. So we can talk about function of x, function of a random variable. Because it is discrete, you can use any function. If the random variable is continuous, we cannot do that. So you can talk about polynomial of x, x square, x cube, and all that, which we will be using later. So now we want to talk about a similar concept called random vector. It's same thing, except the space is, the range space is Rn, that's all. Okay. So if you have a probability space, x omega script p, then x bar, you can call it x bar from omega to Rn or Rk is a random vector. If omega is discrete, then there is no need to say anything further. But if it is not discrete, then you have to say that range of x bar is countable. The same thing, countable. And x bar equal to some x bar. Okay. This set. So if you want, you have to write it as omega in omega, such that x bar of omega equal to some x bar, small x bar, is in A for all x bar in Rn. Well, it will take only countably many values. You have to verify this for countable. For other values, it is just empty set. So you can write it for everything. It's okay. So this is what is called a random vector. Okay. Then notice these are all straightforward observation, but you will just note it. So if I have a function from Rn to Rm, okay, and x bar is from omega to Rn, a random variable, and this is just any function, okay, any function. Okay. Then f of the same thing, f of x bar is also a random vector. Okay. The same proof will work, except that you have to take it as f of x bar equal to some y bar, then x bar equal to x bar, such that x bar is in f inverse. It's just the same proof will work. Okay. It's the same thing. Okay. So you can talk about function of a random vector. The function can be any function. Okay. In particular, you can take the function taking values in real line. So if f is from Rn to R, and x is a random variable. I mean, when I say random variable, it is discrete random variable. I didn't want to. I mean, we will consider continuous random variable after midterm. So till then, whatever I say, whenever I say random variable, it is discrete random variable. So you are assuming that. Okay. Sometime I mean I have forgotten now, so I may forget. Okay. So it is just discrete random variable, which we have to write. Discrete random variable. Okay. Then of course I'm just recording it. F of x is also a random variable. No. Oh, yeah, f from Rn to Rn, and x bar is a random vector. It's not writing random vector. If you have a random vector and f is a function from Rn to R, then f is a random variable. Random variable is also a vector only. It is just one dimensional. So it's also a random variable. So this is remark number 1 or something. Remark number 2 is if x is equal to x bar equal to x1, x2, some xn. Okay, where x bar, x1, xi are from omega to real line. Okay, then x bar is a random vector. If and only if each xi is a random variable. Okay, proof is direct. So you can just take some n random variables and then get a random vector out of this like this. So first this way, x bar is a, maybe you will prove this way. Each xi is a random variable. Xi is a random variable for all I. Okay. Then x bar, this set, x bar equal to some, I mean, I write it here instead of small x bar, I write it like this, xn. Okay. This is equal to intersection of I equal to 1 to n, xi equal to xi, right? This is equal to means each coordinate should match, and this is just this. Each set is in ai, each set is in a, so the intersection is a is closed under intersection, so it is also in a. So this is the B. This set is in a. This set is in ai, so because of that. So we are taking intersection. So if you have n random variables, you can get a random vector like that. Similarly, we have already proved that you can take function of any random vector and get a random variable. So if you take pi from Rn to R as just the coordinate projection, ith coordinate projection, that is just x1 up to xn, xi to xi. Okay, then pi of x bar is xi. Okay. So because of that, from the earlier one, it follows. So this implies xi is random. It's okay. I went very fast. It is just you can take n random variables and you can write it like that, and you get a random vector. Okay, if each xi is a random variable, then you take the intersection. Because of that, that's a random vector. I mean, you have to say that this is in the sigma algebra, and you take the intersection, and you get that as the random vector. Similarly, if x bar is a random vector, then you project it. You can take any function of the random vector, that's a random variable. You take the projection, that is also a function. So it's a random vector. That's all. Opposite direction. Yeah, I wrote it like that. Good. Yeah. Initially, I first proved that. Yeah, that's right. Yeah. Okay. Okay. So if you have a random vector, then we consider what is called a joint mass function. You have a mass function. So here you have a joint mass function. So if you want to write, I will wait for it. we have a probability space in the background always. Random vector, okay. Discrete random vector. Okay. So let x1 bar, xn bar is the range of x bar. Okay. Then you define the function, okay, at, I mean, this is equal to xi bar equal to the probability of x bar equal to xi bar. Okay. All those omega such that x bar omega equal to x bar. Okay. That's what it means. Okay. And f of x bar equal to 0 if x bar is not in this set. Okay. You take the range of that, in the range space is defined like that, otherwise it's 0. Okay. So you get this is what is called joint mass if x bar equal to x1, x2 up to xn. Okay. Okay. So let me say you have x bar which is defined from omega to Rn. Of course, x bar will be given by some x1 up to xn as we have seen. Okay. So x bar will be given by n random variable. Okay. Then you take the range of that. Okay. On the range you define like, and on the range you define this function. This is the probability, joint probability mass function. Okay. This is called joint probability mass function of this x1 up to xn. Okay. If you want, you can keep this x bar here. Okay. I mean, just to note that it depends on that. Okay. In general, when we talk about if you have a random variable x, then you write it as fx, okay, which is the mass function corresponding to x. Okay, you can write it like that. I mean, when it is clear, we don't write. Otherwise, we just write it. So if you have a random vector, you denote it like this. Then if you are given a joint probability mass function of some random vector, how to get the mass function of each random variable? Okay. So this is the proposition. Let's see. Proposition. Let fx bar be probability mass function, okay, function of x bar, okay, on some omega 3. Okay. Then and x bar equal to this, x bar equal to x1 to xn. Okay. Then the probability mass function, I mean, this is the joint probability, joint function of xi. Well, it's better to take one. Anyway, I'll write it. Okay. Xi is equal to fx bar, okay, of so you have to fix the I and sum over everything else. Okay, all those x bar, okay, the summation such that x bar equal to probability mass function of xi, which I denoted like f of xi at some x. Okay, so this is equal to summation x bar equal to x1, x2 up to x, the ith position. Okay, then up to xn of f of x bar of x1, x up to xn. Is okay. I mean, the statement is clear. We'll see the proof, which is very easy. I'm just saying, if you are given the joint probability mass function, which is a function on Rn, mostly 0, it is just non-zero uncountable number of points. Okay. And of course, there is another property that it is greater than or equal to 0. I haven't listed out the property, but we'll come to that. Okay. So then if you want to compute the probability mass function of any one random variable, okay, for example, if you have only two, if you have only x and y, if you have x and y, okay, these are the only two random variables. Fy, xy is given. Okay, then you want to compute fx, then fx of, so fx will be in two variables, right? Ij. Okay, then fx of I equal to summation over j f that xy, the joint one of ij. Okay, you sum over the j. That's what I have written. It's written, no? There is no mistake in that. Okay? If you have only two random variables, xi and x, I mean x and y, okay, or xi and xj if you want, okay, then f of ij, it will, the range varies from I and j, or I mean xi, xj doesn't matter. Okay, if you want xi, x1, x2, okay, then I have to. It's better ij. Okay, it's okay. If you are given the joint random variable, which is a function of two variables, you sum over the first variable and get that. That's all. Okay, this is what is called marginal. Okay, you get the marginal from this marginal distribution. If this is the joint distribution, this is the marginal distribution, which gives the distribution of this xi. You have a random vector, which is a random, I mean, it's like a random variable taking values in Rn. You sum over all the other indices except one, you get a random mass function on R. Okay, that is a marginal distribution. Okay, it's called marginal. Marginal distribution. We will study this again. Here it is just for our record. So proof of this. Actually easy to prove. Okay. So we want to compute fx at some x, okay, which is equal to probability of x equal to x. Okay, all those omega, I mean, this means all those omega such that x of omega equal to x. That's what this means. Okay, I've just written it like this. But this is equal to this. This is a set, right? Probability of this set. Okay, this is okay. Yeah, I should have put this probability of this set, which is same as probability of intersection omega, the original omega, right? Yeah, here you are saying ith coordinate fixing. Ith coordinate is x. It's clear. Ith coordinate is f xi x equal to f of x is fixed in the ith coordinate. This is comma. This is comma. Okay. that is comma. Okay. X ith coordinate is x. Everything else is x1. Everything varies. Okay. You sum it over. That's all. That's what you have here also I have done. Okay. First coordinate is fixed. You sum over the second coordinate. Here it's clear because there are only two variables. Okay. I mean, if you whichever the marginal you want, you fix that coordinate and sum over the all the other. That's all. If there are n of them, if there are two of them, you just have to sum over the one of them. Okay? So to prove that, we take fx x. By definition, this is equal to probability of x equal to x. Okay, that is the probability. So you can take this. This is the whole set. If you take the intersection of the whole set, it is the same thing. Okay, right? It is an intersection. Any set is intersection with the whole set. This is the universal set. This is everything. Okay. So just for to write the next step, I am just writing. Okay. So this is equal to probability of x equal to probability of, I have to say xi, no, sorry, xi equal to, sorry, not x equal to xi equal to this. So xi equal to x. Okay. Intersection xj equal to small xj, okay, and where xj varies over that set, varies over xj is in the range of xj and j not equal to I. Okay. I am just writing the omega as this. Omega is what? It's just all possibility. You take, I mean, this is just j is inside, okay? Except I, you take all j, xj equal to xj, where xj is in the range of xj, it varies over that, right? Is okay. I mean, I'm saying that if you have some function from here to omega to r, it range of x is x1 up to range of x equal to some x1, x2 like this. Okay, then this set x of omega equal to xj, where j is ranges over that, where j for all j. Okay, you include all j equal to 1, 2. Okay, then this is exactly equal to omega, right? All those omega such that x of omega is in the range of x is omega, big omega, right? All those small omega such that x of omega is in the range of x is omega, right? That's what I have written. The trivial statement. I have written the trivial statement. Okay. So x of x intersection omega, which is equal to, this is all those omega. I'm just writing it like that. Okay. Xj is equal to xj such that xj is in the range of xj. Okay. Okay. That is just omega. Now the point is, if you take different j, these sets are, if you take different j, here it's you are just taking the union over all j. For a different j, they are disjoint, right? So this is equal to probability of union of j not equal to I. Okay, not j not equal to I, and also xj is in the range of xj. Okay, and xi equal to x and xj equal to xj. Okay, this is the intersection xj equal to xj. Okay. Is okay. I have just written because this is just the union of all those things, and this union is disjoint union. For different j, okay, if the range is some, I mean, if the range is going to be some particular xj, then it will not be the other xj, right? So this union is a disjoint union for different j, for different j. You fix a xj, you fix a set of except I xj not equal to I, you fix all the other j, one particular tuple. See, I just want to write it as the tuple n minus 1 tuple like this. Where is the bracket in the union? So there are only two sets. Huh? This is the bracket you want. Huh? This is the bracket you want. Okay. Well, this is the bracket. Okay. It is just this intersection. This is just for one I. This is one. This is just for different j. J not equal to I. Sorry. Let's put the j not equal to I there. No. We have to put it here. We have to put it here. Yeah. Or you have to take the intersection n times. I mean, it is like probability of, let's write it. Yeah, let's just write it clearly, more clearly. No, probability of, okay, union of xj1, the x1, x2 up to xn in R, I mean, xn, and such that I not equal to, I mean, in this, there is no I, okay, there is no xi. See, otherwise I have to write the set for each xi. So suppose, okay, let's say that range of x, okay, let me write it like this. Probability of union of x1, xj in range of xj, okay, and j not equal to I. Okay, then xi equal to x, intersection x1 equal to x, maybe x, if I equal to 1, x1 will not be there. Okay, x1 in x1 intersection up to xn equal to xn. I mean, it should be something like that. I had kept it inside, but it just that is just the intersection of all these things. But then this is a disjoint union. Okay? If you have a different j, different tuple, here you are having a tuple, n minus 1 tuple. If you have a different tuple, the set will be different, right? Something is mapping to one point, okay, something mapping to the other because of the well-definedness of the function. Okay, because x is it is because this is disjoint because the function is well-defined. That is what x1 up to xn. I spelled it out, except I not equal to j. That's what I said. I don't want to. If you want, you have j equal to, okay, 1 to n, okay, xi equal to xj, where j not equal to I. Okay, this is okay. This is such a simple thing, but only notationally it is getting messy. There is nothing in this. Okay, if you write two of them, it will be easy. Okay. Yeah. If you take two of them, there is no problem. Okay. For n of them, I am writing it like that. It's better to write it as two of them if you want. Okay. You just sum over the other one. But then, so this is, that is disjoint union. So this is just the sum. Okay. Over all those x1 up to xn, I not equal to, I mean, x1 up to x1 up to xi minus 1, xi plus 1 up to xn. Okay. Of all those, f of x1 up to xi plus 1 up to xn. That's what we wanted. If you just have two of them, it will be easy. I should have proved it for two of them. I thought it will not get messy. You can prove it for two of them and use induction to prove for n. Okay? That's easier. In fact, you can get the n minus 1 marginal. Yeah, then we have to consider n minus 1 another thing. Anyway, this is something very silly, very easy. Okay? So if you know the joint probability mass function of a random vector, then you can get the probability mass function of the individual random variable, which are called marginal. Okay. Okay. So next thing I want to consider is what is called distribution. Range of xj here. Here. Xj is in xj. Yeah. Range of xj, xi is does not matter. It is just x is in range of xi. X is in range of xi, right? F of x is in range. Same thing. If you write it for two of them, it will be easy. Okay, you write it yourself. Yeah, it's just writing it unnecessary. You just fix that coordinate and then sum over everything else. That's all. If for two of them, it will be very easy. You just write it for two of them. Okay? Okay. So next we will discuss what is called a distribution. This is definition. So x is a random variable on omega. Then you define f of x equal to probability of x, probability of this set. X less than or equal to x. That's all. This is same as probability of the set x is in minus infinity to x. I mean, this is mostly useful in continuous case. I haven't said, I said I will be using only discrete random variable, but this is mostly useful for continuous random variable. So this is for any random variable. I'm defining it for any random variable. Okay? So for any random variable, I haven't said, I haven't defined continuous random variable, but notice that This is just a general definition. Okay? There is nothing about discrete or continuous. Okay? Then the following properties hold. Okay, let's say proposition. F is the distribution. This is just a function of some random variable x. Okay. Then first one, f is increasing, which is clear, to limit x going to minus infinity f of x equal to 0, limit x going to infinity f of x equal to 1, and third, that's what I'm going to read. Yeah. So limit x decreases to x naught f of x equal to f of x naught. This is what is called right continuous. It is an increasing right continuous. Okay. F is this distribution. Given a x, you have a f uniquely. So it's clear that minus infinity of x is contained in minus infinity of y if x is less than or equal to y. So this implies f of x is less than or equal to f of y. X is less than or equal to y. Okay. So first property is clear. Second property is minus infinity x. Okay. This decreases to empty set as x goes to minus infinity. Okay. That's clear. Minus infinity x will decrease to this. So we know that probability function are continuous with respect to increasing and decreasing. I mean, increasing union and decreasing intersection. So, and intersection of minus. So this implies probability of this will increase to probability of 0. So this implies f of x decreases to 0 if x goes to minus infinity. Okay. Limit here. This is a number. X decreases to. This is a notation, you know, no? You don't consider something less than x naught. You consider, or you, if you want, you can take sequences f of x plus epsilon. Okay? Exactly. Epsilon goes to 0. Okay? If you want it like that, or you take 1 by n and do that, because it's the limit will exist here. Okay, that's another thing important. If it limit doesn't exist, you cannot use sequences. But since the limit exists, you can just use sequences 1 plus n. I mean, the limit exists because of the what we are going to prove. Otherwise, you cannot just take one sequence and do that. This one. Here. Right continuous. Yeah. So you should listen to what I say also. I said it right continuous. Okay. Right continuous. RIGHT, right continuous. So everything follows from our monotone property, the continuity of the probability function, okay, with respect to increasing and decreasing, increasing union and decreasing intersection. Okay. Then the second one or third one, second one is so minus infinity x plus epsilon. Okay. These sets, if you take these sets, I have to take this, will decrease to minus infinity x. You should be just careful with this. Minus infinity x plus epsilon, which will always include x. I mean, if you take the intersection, this just means that intersection of minus infinity x plus epsilon equal to minus infinity x. That's what this means when we say this is decreasing. Okay. If x is here, then it will be in all those minus infinity x, so it is here. That will include x also. If it is open interval, it will not. I mean, sometime I mean, here it will work. Yeah. I mean, for the left hand, it will not work. I'll just come to that. Okay. So because of that, this implies this is f of x plus epsilon. I mean, it's an increasing function of x. Huh? The third property. 1 second. Right continuity. Oh, I forgot that. Okay, that is same as this. Okay, minus infinity x will increase to minus infinity infinity as x tends to infinity. Okay, so this implies f of x will increase to 1. Minus infinity is r, and which is whole probability of whole set is 1. Okay, will increase to 1. Okay, that is clear. The same as that. Here also, this is also same as that. Okay, here it is just minus infinity x naught plus epsilon will decrease to that. Okay, this implies f of x. That's all. That's what we want. This is what right continuous means. Okay, we have proved all the 3 properties of this. So any function which satisfies these 3 properties can be called as a distribution. But then it's a long proof that, see, if you have any function like this, which satisfies these things, similar to Riemann integral, using Riemann-Stieltjes integral, you can make sense of probability of some AB, which is just the Riemann-Stieltjes integral of this. Okay, or you can include that. That's big, depends on whether there is a mass at that point or something. This is equal to integral of some, I mean, integral of just df between a to b. Okay, by you know what is df? This is Riemann-Stieltjes integral. Instead of b minus a, you should f of b minus f of a in that, and then you use the same thing. But you can make sense for integral, but you can't. You to make sense of any set, you need measure theory. Okay, so without measure theory, we cannot prove the other way. If you are given a f which satisfies all these conditions, then there is a probability measure satisfying. So then there is a probability measure, and random variable is clear. You can just take the identity function and get a random variable. There is a probability measure on R such that the distribution is given by this. Okay, that you can prove. For that you need measure theory. But in our case, when so the proof is over, when x is discrete, this f is just a step function, right? It will just have jumps. Okay, and you can, so by using the difference, you can calculate the point. So if f is given, okay, then the probability of x greater than x equal to 1 minus f of x, right? Probability, this is equal to probability of, I mean, 1 minus probability of x less than or equal to x, right? It's just the complement of this. This is equal to x less than or equal to x complement, okay? And that is equal to this, okay? So you can calculate that. Also, you can define f of x minus equal to limit of epsilon goes to 0, f of x minus epsilon. Okay, this limit will exist because this is just equal to, I mean, this is just, I mean, this is just this is f of x minus epsilon equal to probability of x less than or equal to x minus epsilon, right? Which is just, I mean, which write it as the interval. Probability of this set, x is in minus infinity, x minus epsilon, okay, which will be equal to probability of x is in this set, minus infinity, x, this open interval. No, it's not about discrete. Generally, I'm saying this statement. This statement, this is true all the time. Huh? This one, which one are talking about? Huh? is equal to this.
Greater than or equal to it.
Greater than or equal to x, yeah. What are you saying? X is greater than or equal to x, equal to this. Yeah. That I am not talking about. Yeah. It may be, there is nothing like discrete continuous. Things may be combined also. Okay. If you, what you are saying is purely continuous. Yeah, that's right. Then that is true. Yeah, that's right. Okay. This is a general statement. For discrete thing, it's a step function. That is a statement here, and we are done with it. This is general statement. I mean, these are all just observation. Okay. There is nothing. There is no idea involved in the proof. Okay. It's just observation. Okay. So f is given. F is some distribution. Then a probability of x greater than x, you can find it like this. Okay. And then probability of x less than or equal. I mean, probability of x minus is just which is equal to this. Okay. Then f of x minus equal to probability of I have written x less than x. Okay. I mean, if you define x minus equal to this, which exists because it is the intersection of all those things, right? I mean, that's because f of x minus epsilon, which is just I mean, it is because this set minus infinity x minus epsilon, this set will decrease to will increase minus infinity x minus epsilon will increase to minus infinity x, the open interval x, right? I mean, it will contain all point till x, but it will not contain x. So because of that, this minus infinity x minus epsilon, this half, this here it's closed interval. Okay, this will increase to that. So probability of this will increase to probability of this. So because of that, this limit will exist. That is why this limit will exist. Okay. So since this limit will exist, that is exactly equal to probability of x less than x. Okay. And probability of x equal to x equal to f of x minus f of x minus. As you say, when it is continuous, this is equal to 0. Okay. When the distribution is continuous, this is equal to 0. I mean, you said the function is continuous or the distribution general problem. Okay. So f is continuous. If the function f is continuous, then this is 0, and the probability of any point is 0. Water here, it's okay to drink. So for discrete function, you can add it. I mean, discrete function f of x is just equal to summation f of xi, all those countable points, such that xi is less than or equal to the integer part of this. Okay? You just add up to that. Okay, for discrete one. So there is something called median. That's what I want to define. Okay? I mean, this is some vague definition which is used in statistics, but you better know that. Okay, so f of x is a distribution of some x. Okay, then x in R is said to be a median. There may be more than one, as we can see, is a median if probability of x. Huh? What? Xi less than or equal to this. I mean, x is discrete. Okay? What is not true? Yeah, discrete. Otherwise, how will it be true? This will. I said probability mass function. We define only for discrete one. Huh?
No, it is. I think it should be. You cannot use that.
Cannot use what?
Like the discrete maybe like 0.5 or 1, 1.5. 2. And X is more of X and X.
Yeah. Exit from what?
I think you should make F4
Huh.
Xj. No, you can't use that.
Now I am just saying you count from minus infinity all those xi's. You count those f of xi. Yeah, I'm not saying it is integer. Ah, okay. When it is integer, okay. Okay, you are right. So this is your problem. Okay. When it is integer, it is like that. Otherwise, all those things such that xi is less than okay, x. Okay. This is okay. Yeah. X is fine. Yeah, I had integer in mind and wrote it. Yeah, sure. Yeah, the jumps may not occur at integer, but if you have an integer valued random variable, then that is correct. So we call some point as a median if x greater than or x is greater than or equal to half, okay, and probability of x x less than x less than or equal to x is half, x less than or equal to, that's what I have written, x greater than or equal to x is also greater than or equal to half. Okay. I mean, this has an intersection only at the point x. Maybe it will happen at that point. Okay. So this is called a median. If it is discrete, it will be clearly there will be one point, unless at that point the probability 0.5 is reached. Then till the next point, all those points will be median. Just think about it. So it is something like if you have discrete one, if the probability of up to here, probability of all the points, distribution up to here is 0.5. Okay, then any point here will be a median up to the next point. If the probability here increases from some 4.9, I'm sorry, 0.49 to something more than 0.5, then this point will be a unique median in the discrete case. In the continuous case, it will be totally different. So there may be many median. This is called a median. This is used in statistics and okay, it's just a definition. We will not use it. Okay, don't worry. Okay, let's go to better interesting things. Okay. It's just I want to record this definition. That's all. Okay. This is the definition of median. Okay. So now we want to talk about independence of random variables. Okay. So this is the definition. So if we have two random variables, x, y, random variables on the same probability space, then only we can talk about this. Okay. Then we say x and y are independent. I mean, it's important that they are discrete random variable. A discrete random variable. If it is just the mass function multiplies or probability of x equal to x. Okay.
There is always significant that is uniquely.
When the jump occurs, huh? No, I'm not saying that. This is not unique. Median may not be unique. What are you asking? Median may not be unique. Suppose, I mean, even in the discrete case, it may not be unique. Continuous case, it need not be unique. I mean, continuous case is non-discrete case. In the discrete case, suppose the jump occurs at 0.5. Jump occurs at some point, and suppose if it is 0.5, then any other point till the next jump is a median, right?
Oh,
right?
no,
So,
such that x belongs to.
X belongs to what? Huh?
A median, which is a result of random variable.
Which is,
It is in range of.
yeah, it's in the range of the random variable. That's what I said. It need not be unique, no? Median is by definition, it's in the range of random variable. Okay, that median, yeah. I mean, the probability can be 0 after that, no? If you have at x the median occurs, then at y also median. If the probability of any point here is 0, then all those points will be median. You want to talk about range? Within the range, it will be, okay, you are asking, that's what you mean by range. Okay. I think mean the range of a discrete random variable, it's unique. Yeah. Yeah. Yeah, it looks so. Okay. Yeah,
When we say median, we mean the median in the range.
correct.
That is unique.
That's unique. Yeah. Wherever the 0.5 occurs, I mean, wherever the addition f of x becomes 0.5. Exactly. Okay. I mean, the thing is, if you talk about this f, then it, I mean, if you are given only distribution, then it will not equal to. No, it can be six. It can be more than half. At x, suppose if it increases, the probability of x is equal to some more than. I mean, it was for 0.49. Suppose this is some 0.2, then exactly at 0.5 it will not occur. This such a set may not be there. Such a x may not occur, may not be there. That's all. Okay, let's forget median. Let's talk about independent. Okay. So we have two random variables, x and y. We say x and y are independent if probability of x equal to x intersection probability of y equal to y. This is for discrete case. Okay, is equal to probability, the individual probability. Multiplication of the x equal to x times probability of y equal to 1. Okay. This is the definition of independence. Okay. So this implies the following: x, y independent. Okay. Then, I mean, they are discrete random variables. I don't say all that. Then probability of x in A, y in B, where A, B are in the range of that or whatever, okay, equal to probability of x in A times probability of y in B. I'm saying this is just for single point. That's the definition. Then it holds for all sets A and B. Okay. Hmm? What? It's fine. So the proof of the corollary is clear. I mean, this is corollary to definition, immediate. Okay. A corollary is usually for a theorem or proposition. This is immediate, maybe a remark we can call. Okay. So probability, let me just write it. Probability of x in A, y in B. Okay. We can assume that A and B are countable set, which is equal to probability of union of I in A, J, B, probability, and this is x equal to I, y equal to j. Okay. Then that multiplies and all that, you take it, use the definition, and that is, but these sets are disjoint set. When you have different points and these sets are disjoint set, this is equal to summation over ij, okay, I in A, j in B, okay, then the individual probability, which is equal to probability of x equal to I, then probability of y equal to j. Now you do the summation inside, you take this summation first, sum over I, and this will get, okay. I'll just write it, and then if you have a problem, you just tell me x in A times probability of y in B. Okay, let me, I will just explain now. Okay. The claim is probability of x in A, y in B is equal to, it's just the product of probability of x in A, probability of y in B. Okay. I've just taken it like that. This set You assume that it's countable. If it is uncountable, this will only be a countable union because it will be, I mean, set can be uncountable, but then the union will be, because we don't care, the probability is 0. It will be, okay, that will be empty set, right? Okay. So, I mean, A can be uncountable, but X equal to I, that, I mean, it's only those countable things which matters. So you can write it like this, disjoint union like this, I in A, J in B, like this. Okay. So then you can take the product of these things like that. Since they are disjoint, you write the sum like this. Now you take this sum, which is will be union of here. Oh, that is just all those omega such that x of omega is in A and y of omega is in B. That's what it means. I said no. I will write freely like this. When I said probability of x in A, y in B, all those omega such that x of omega is in A, y of omega is in B. Okay, I fixed that notation. I will freely write like this. That's what it means. Small. This should be capital. You are right. Sorry. Is that your confusion? Okay. There is no small y anywhere. It's all capital Y only. Okay. Okay, so proof is clear. We just multiply it and that's all. Okay. So this is a real proposition. X, Y are independent. Two random variable, discrete random variable that are independent. And F and G are some function from R to R. Okay. Then F of X and G of Y are independent. So proof. So we want to prove, we are given X and Y are independent. We want to prove F of X and G of Y are independent also. So for that, we have to consider probability of F of X equal to some X, it's okay. And G of Y equal to some Y. Okay. We want to consider this probability. And that is same as, put a bracket if you want, that is same as the probability of, so this is just a union. I mean, which is same as saying probability of X is in F inverse of X, singleton X. Okay. By this, I mean all those points which maps to X, okay, which is a pre-image of X. And Y is in G inverse of singleton Y. Okay. Is okay. Now we have already proved its product over any two sets, any two different sets. Now this is equal to probability of X in F inverse of this set times probability of this set. Okay. Y in this G inverse that Y. Okay. Now this is just equal to, if you want, this is equal to probability of F of X equal to X times probability of F of G of Y equal to 1. Okay. That's all. That's what we wanted. Okay. So it's clear. I should leave this as exercise. Okay. So if X and Y are independent, then F of X and G of Y for any function, they are also independent. Okay. Yeah. So we wrote the definition of independence. That basically means that the probability mass function of the random vector just multiplies, right? I'll just state that. So this is just a remark. Okay, there is nothing to prove. If X and Y are independent, two random variables which are independent. then you consider the probability mass function of xy, okay, as a random vector, two vector, okay, two vector of any two things is equal to fx at x times fy at y. I mean, I erased the definition. That's what precisely. This is just the definition. Okay? So the probability mass function is just the product. That's what it means. Okay. So this is just to notice. I mean, this is just a remark we should remember. Okay. How much time I have? Let's see an example of independence. Before that, I want to say this is also a trivial remark. So one thing I forgot to state is, so I said that if you are just given a probability mass function, then you have a random variable with that probability mass function. I mean, in the sense that if you have any function which satisfies f of x, this I stated, no, f of x greater than or equal to 0, and f of x is greater than 0 only for countably many points, and summation f of x equal to 1. If you have any function, then there is a random variable with mass function f. So similarly, if we have a vector, some function on a vector space, f is from Rn to 0, 1. Okay, if you have some function, okay, Rn, such that f of x bar is greater than this, f of x bar is greater than 0, only count for countable. Okay, I mean, I will not state this because it's the same thing. Okay, countable, and summation f of x bar equal to 1. Okay, then there is a random vector, then there is a probability space and random vector and all that. You just take the range of this, all those f of x bar equal to, suppose that is equal to x1 bar, x2 bar, something like that. You take this as omega and take the identity function, that will give that. Okay, same proof. Okay, so given any mass function, you have a random variable corresponding to that. Okay, so you can freely talk about that. But then if you are given two probability mass functions, just to one-dimensional one, okay, so this is the proposition. So before that, let us notice something else. What is the example of independence? Okay, independent random variable. You have a dice, and you can do two different experiments and say that you can do something and associate with that. Okay, that is like taking direct product. Or you take a pack of card, one card you take, you sum over all those 1 to 13, or sum over 1 to 4, whether it is you associate some number, if it is dice or dice, no, dice or spade or something. Okay, according to that you assign or some add all those things. See, if a card is something like 1 to 13 cross 1 to 4. Okay, you have a function on this, you have a function on this. They will be independent. Okay, so in general, if omega equal to omega 1 cross omega 2, you take omega 1 cross omega 2. Okay, and let's assume it's discrete something. Okay, so then you define a function from omega 1 to r. Okay, g from this f, maybe, I mean, you shouldn't confuse with probability mass function. Okay, maybe I should use it. I mean, this f is just some f. Okay, it's not, this has nothing to do with the mass function. Okay, omega 2 to r. Okay, then you define x from omega 1 cross omega 2. Okay, such that to r by x of omega 1 omega 2 equal to f of omega 1. Okay, and y of omega 1 omega 2 equal to g of omega 2. I'm just saying you take a function in the first set, okay, or you have a function on the only on the first coordinate, and you define function, but this is different on two of them, but it depends only on the first coordinate. Okay, then these two are independent because you compute the mass function, it will multiply. It's clear. Okay, but the point is, this is what I want to state. Proposition. You are just given two mass functions. Let f1, f2 be two probability mass function. That is, it's greater than or equal to 0. It's strictly greater than 0 only at countable points. And if you sum f of x over everything, it just adds up to 1. F1 and f2 are like that. Then there exists a omega script A, P, okay. I mean, it will be A and all, doesn't matter. It's just power set, okay, for us when it is discrete. Okay. P such that and x comma y function random variable from omega to r such that x and y are independent. So if you are given any mass functions, then there exists any two mass function, maybe f1 equal to f2, maybe they are same also. Okay, you can take same f1 equal to f2 also is possible. That's be any two probability mass function. Then there exists a probability space such that x and y are independent. The proof is again very easy. Proof. Huh? What less than? There is no less than. This is this one. This is such that my notation. Such that. Okay, such that. Yes, such that or something. This is what I'm used to. Many people use this notation. Yeah. So this is if you attend more classes at CNI, you will get used to it. Yeah, I'm sure many people use it. Because I didn't invent it. I just copied from someone. Okay? So I think you are used to it because you are in the second semester. This is there exists. This is such that. This is for all. I hope you know all this. This and this. It's clear they are different. It's clearly they are different. This is there exists. That then you will ask for all letters. No, I mean. Okay. So let range of it's countable. So range of not range of f. Let x1, x2, x1, x2, all these points. Because all those points x and r such that f of x is greater than 0. Similarly, y1, y2, something. This is equal to y in r such that g of y is greater than 0. Okay. Call this as omega 1 equal to this, omega 2 equal to this. Okay. Let omega 1 equal to this, omega 2 equal to that. Now it's clear what to do. Take omega equal to omega 1 cross omega 2. Okay. Define x, y from omega to r by x of omega 1, two variable function, omega 1, omega 2 is just omega 1. And y of omega 1, omega 2 is just omega. It is just the projection onto the coordinate. Okay. Is it clear? Then that will have the probability mass function. X will have, okay. And okay, I have to say what is the probability. Okay. Probability of, so x is omega 1 cross omega 2, and I should say probability of, okay, and p of, I mean, this is the small p. Probability is same as mass function. Okay. It's clear now what is the probability of this. Okay, I don't have to write. Probability of any point omega 1, omega 2, probability of small p of any omega 1, omega 2 is equal to f of omega 1 times g of omega. Okay. For any, I mean, probability can be defined for points in the discrete case. Okay. This is discrete. Okay. So for any set, you have to add over all the set, all the points in the set. Okay. So it's clearly x and y are independent, right? Check. Convince yourself. Independent. That's clear because the probability mass functions are exactly that, and that multiplies because of that. It's clear. Okay. Okay. So this is about independence. I have only 10 minutes. I thought I will see an example, something slightly interesting, but I may not have time. It will take at least 15 minutes. Now this is fast, so I have only 3-4 minutes, I think. Okay. I will just define what is an expectation and quickly prove something. Okay. This is definition of expectation. This is for only discrete random variable. Okay. X is a discrete random variable. defined on probability space. Actually, we don't have to worry about the probability space at all when we want to talk about the expectation. Then the expectation, what you expect to happen, but what you expect may not happen most of the time, because expectation can be a fraction. You may have integer valued number and the expectation may be a fraction. Okay, so it will not happen. It is just it's called expectation. Okay, it is just a definition. Expectation of x denoted by, with respect to that probability space, so it is denoted by e of x or ex simply. Okay, no, I have to say when it exists. Sorry, we say the expectation exists. Expectation may not exist. Okay, exist if summation over I mean, just write it x in R, but it is 0 for almost all of them. Okay, x times probability of x equal to x. Otherwise, I have to enumerate the range of x and other things. This is okay, no? This is over uncountability, but it's actually over countability. Okay, here you have mod x. This should be less than infinity. I mean, this should not diverge. This is a series, no? It's a countable sum. It can diverge. So when it is less than infinity, we say the expectation exists. Okay. Then E of x is defined as the expectation. Then the expectation E of x is equal to summation x in R, x times probability of x equal to x. Okay. I mean, this is just sum of x times f of x, right? I mean, this is just mod x times f of x. F is the mass function. Okay. That sum should be less than infinity. See, the point is this sum can be infinite, but this can exist. But then there is no well-definedness for this. It depends on the arrangement. It will depend on the arrangement. But then you cannot define expectation depending on how you count the points in the expectation. You are so much worried. As far as you understand, it doesn't matter. Okay. I mean, I'm too lazy to write the full thing. I mean, when I say function, I just write it like this. Okay. So you should understand that function. So it is similarly, it's something, whatever I just give you a hint what that word is. Okay. We don't use any other word, exception or something. We only use expectation. Even saying it is, I'm too lazy to say that, such a long word. It should be short. Okay, it's clear. The expectation, the definition is clear. Okay. So now let me prove, and I want to prove something. So within just next 2 minutes. What?
Okay.
What's the problem? You can arrange to get a convergent series. In that case, it doesn't exist. If it is infinite, expectation doesn't exist. We define expectation exists only if that sum is less than infinity. The reason is, otherwise, you see, you don't count the number of points in some order, no? You can't rearrange and say that the probability space, you have some points, I will count it in that order. There is no order in that. Okay, so you shouldn't rearrange and do that. So that is not well defined. So few things are not well defined. It's not well defined. That's what it means. Okay. Now quick proof. Proposition. So if okay, let me just first say this: x, y are independent. This implies E of x, y. You can take product of two functions, right? We have already said. Okay, you can take the random vector and take the product. Huh? No, expectation of x times expectation of y. What x square and the? You are talking about some variance, something. You have gone into that. Yeah, that will come to that later. Okay, some formula about variance. No. Is the expectation of x and y, it just multiplies. Okay. That is clear. Shall I leave it as an exercise? Expectation is this probability of x. Okay, you will have xy here. Okay, then you just sum it over xy, x equal to xy. Then that set multiplies. Okay, then it's like that, right? So similarly, proposition. If xy are independent, I mean, the question is whether the converse is true. Converse is not true. So for that, we need if and only if expectation of f of x, g of y equal to expectation of f of x, expectation of g of y. Okay? If this is true, then they are also independent. It's the true the other way. For all function, for all fg. Okay? In the continuous case, only some particular kind of function will be allowed. Here you can take all function. In fact, you need only one function. I mean, not one function, one particular type of function. Okay? So this way is clear because we have already proved that if x and y are independent, f of x and f of y are independent. So this follows. Okay? Because f of x and f of y are independent. So it follows. We have to only prove this way. To prove so for that you note, see for all function take f is equal to 1. So let me write. So suppose range of x equal to some x1, x2 like this. Okay. And similarly, range of y equal to y1, y2 like this. Okay. Then you take the indicator function of x equal to xi. Okay. Indicate the function of this xi, singleton xi of x equal to indicator function of, let me write it and then explain it. Okay, of all those omega such that x of omega equal to xi, which is x equal to xi. Okay, I mean whatever x equal to xi. I'm writing it so that we will see the proof. Okay? This is a function. Indicator function of xi is a function from R to R, right? It takes the value 1 at xi and 0 everywhere else. That is what this indicator function is, right? Which is a function from R to R. This indicator function xi of this x is, this should be, this is what, that's why I wrote 1. I mean, I usually write 1. So, okay. This is the indicator function of this set. This is from the probability space. Is this clear? Okay. And similarly, indicator function of yj of y equal to indicator function of y equal to y. Okay. Now you apply the, I mean, apply the fact that f of x and g of x are, this is your f, this is your g. You apply that, you will get that independence of x and y. Shall I leave it as an exercise or we can do it next time? Next time? No, it's clear. I thought you will do it as an exercise. Just verify this. This is just a straightforward statement. Okay. This is just the composition of that function, no? X of omega goes to xi. And indicator function xi, there it is 1. You take a omega. You just have to prove that these two functions are same. Okay. This is a function on omega, right? You have composed x and another function. This is a function of omega. So I of x of omega will, if it lands in xi, it is going to be 1. Otherwise, it is 0. Okay. Here also it's the same thing. If the omega lands in xi, it's going to be 1. It's only on this set, right? Otherwise it is 0. By definition, these two functions are equal. I've just written it in different way. This is your f, this is your g. If you assume this condition, e of f of x, g of x equal to this, there is f of x and g of x satisfy that. That will imply the definition of the independence. Straightforward. Okay, I will recall it. If you don't understand, you will do it in the next time.